So we're going to start in looking at meshing. We're going to do a 3D example that covers sort of a variety of meshing issues related to geometry and building up the geometry. And so these examples are an examples meshing surface NURBS. There's a README there. There's one specific related to contours, one for DM, one for merging surface. But we're going to do this subduction one, which is a 3D subduction zone. So it's a little more complicated than what Charles went over this morning. So there's a README file. And so there's multiple steps here. So the first one, there's generating the surfaces to create the geometry, then using those non-planar surfaces to create the 3D model. So the first one is, I believe this is the fault. This is the subduction interface, and we're going to use sort of horizontal contours and vertical profiles to make up the mesh surface. And so Charles is taking these from some geometry specification of the fault surface. And so what I'm going to do is I'm going to load up this file. So it's interface net surface. And this is a Python script that creates the journal file. And so the parameters are, it's going to take these interface points. And we've simplified this down to just the bare minimum of what makes sense to even create a spline curves from. So we have very few very few contours, very few vertical profiles, and that's just so that when we create these surfaces within Qubit, it doesn't take an hour to run. It runs in a few minutes to do the geometry operations. In reality, you'd have many more points, but this gives you the workflow of how you would set this up. So within this, so we have 4 contours, 3 points per contour. We're going to output to a file called interface netsurface.journal file, and then that journal file will create a ASYS surface file, a geometry file called interface surf.sat. And that will allow us to Qubit will generate the surface, export it, and then we'll re-import it later into Qubit. So instead of sort of building things up all at once, we're doing it in pieces so that, we create our surface, we save it, so then later we can, change the size of our geometry and in terms of the domain, and then we can, because it does take a while to create, it takes a few 10 seconds to create the surface. Instead of having to regenerate that all the time, we save it so that we can come back and use it whenever we want. So this is just Python. You'll notice that, it's using the apropos. So within a Python script, creating a journal file. So we're using a script to write a script that does what we want. But you'll see, there's Qubit commands embedded in here. We could have done it all straight in Python. There's not a whole lot of difference between using the Python interface to Qubit. You use the Python to write the command, but you still got to have the commands in there. So there's not a whole lot of difference between using a script to write a script and doing it in Python. But here I'm going to run the Python interpreter on interface netsurface.py. So it has created my journal file interface netsurface.journal. So within Qubit now, I'm going to go in and I'm going to open up that file. So here is that file. So first it does a reset. It's going to create vertex. I'm going to save the ID of that vertex. It's going to create 3 vertices. And then so I'm going to save the ID of the first vertex, save the ID of the last vertex, create the spline curve, and I'm going to go use the vertices from the beginning to the end, and then I'm going to delete the vertices because I just want to save the curve. And then it does, and then I'm going to save the ID of that curve. And so I'll play up to that point. So there's my first curve. And then I do sort of the same thing for the other curves. So you can see I have my nice horizontal contours. And you'll notice that the error, if you have an error, there'll be a little icon here that looks like a little bell warning you that you've had errors. So far no errors. Now I'm going to do, I think these are the vertical profiles. So there's the vertical profile on the end. I do the other vertical profiles. So now I have 3 vertical profiles, 4 horizontal contours. And so this it basically forms a net. You can think of this as a net. I have lines going one way, lines going basically not perpendicular, but essentially going somewhat orthogonal in terms of logistical layout. And so now I can create a net surface I specify which curves are going in one direction and which curves are going essentially perpendicular. And it'll create a spline surface here that is essentially made up of those surfaces, from those curves. So the more points you have on the curve, sort of the greater spatial variation you can have. So this is how we created a surface using both horizontal and vertical profiles. And then we'll delete the curves, export the interface file. So there we have we've exported just the interface to the ACES file format. So that was our first step. So let's go back to our README. So then our second one, that was our subduction zone interface. Now we're going to splay fault. And we do the same thing in terms of, we're going to use a script to write a script. So splay skin surface. This one, a skin surface, instead of using a net surface, we're going to do a skin. So it's just we're going to give it a series of, I believe it's vertical profiles that then get formed into a surface. So you don't have to have sort of the interconnecting curves. You can just give it a suite of contours and they'll sweep them together into a surface. It's called skinning the surface in terms of how Qubit refers to it, Qubit and Trellis. So this is pretty much the same type of script. So it's splay skin surface Python. It created the splay skin surface journal file. So you can see it looks very similar in terms of we create a vertex, we save the vertex, then we create a spline surface, delete. I'm sorry, this is the journal file. To actually run the journal file, I need to be in Qubit. So close I'll open this up. Display skin surface. So here we are. So there's my single first one. And we'll do another. So there's my two lines, vertical lines. There's a number of those. I create the curves. So here you can see my suite of curves for the splay fault. Then I create surface skin curve and then just list the IDs of my first curve, last curve. And so there's my splay fault. And I should point out that if you downloaded PyLith 2.0.0, this script looked different because in previous versions we went straight from creating splines directly from the list of vertices. When Charles tried to run this script with Trellis, he got errors. It used the first vertex and last vertex for the spline. It didn't, or the last two. It was the workaround for something that Trellis couldn't do, which appears to be a bug, is to go back and create vertices and then use the vertices to go into a spline. So this was our workaround, and so this script in 2.0.1 should work with all current versions of Qubit and Trellis. So that's it for our splay faults. We're going to now do the topography. So going back to our README, the topography, it's also a net surface. I believe it looks very similar to our other journal files. We do sort of the U lines and the V lines and then create a net surface. So I'll just run this script. And I've created topobath net surface. So let's go back to Qubit, load up net surface. Looks very much the same. Reset, create the vertices, create the splines. So there's not a whole lot of topography here. You can barely see that I think there's a little bump in there somewhere. But the idea is you do the same thing if you had greater topography. And most DEMs have sort of a uniform resolution, so that's why the U and V lines works pretty well. We'll export it. So there's our surface. So now we have three surfaces, non-planar surfaces. We have our subduction zone interface, the splay faults, and the surface topography. So this is our main geometry file. Now we're back to sort of more familiar territory of just using the journal file. We're not going to use any more of the Python to generate the script. Again, we're going to use SI units, reset, and now we're going to create our block. And here you can see how I've put the dollar signs out in front of my apropos commands. I haven't actually created my block yet. So there's my block, my brick. And you'll notice that after I create something, a geometry object within Qubit, I can then get calling the function, apropos function ID with the name of the type of object that was being created, I can get the ID of what the object was that I created. So that way I don't have to look up what volume number my block or my brick was. I can store the ID, and then later, if I want to move that volume or so forth, I can just use that variable that has the ID to refer to it. So here I'm going to move it. I'm moving it around a little bit. Move it so Qubit will automatically stick the center of the block at the origin. So now I'm sort of, moving it down. There was some local coordinate system that the geometry was built in. And so I've moved it horizontally 50 kilometers, y 0 direction. I moved it half the block height down so that now the ground surface is, or the top of the block is not quite, so if I move it half the block height down, then the top of the block will be at 0. I'm going to slice off the top of the block using my topography, so I move the block up a little bit. And you'll see that. So the next thing I'm going to do is I'm going to import the surfaces that I created before. So here's my surfaces that I created before. Notice that we have a little bit of a slope to our topography bathymetry. So what we'll do is we're going to slice off the top of our box to be consistent with the topography using the topographic surface. Then we'll come in and we will slice it with the subduction zone surface, and then we'll slice it with the splay surface. So to slice the volume, we use a web cut. So we're going to web cut our big volume with sheet surface 7. And so if I look up, I can show you what my sheet bodies, volume 2, sheet surface 7. So my topography bathymetry surface is surface 7. That's what I put here. So I'm going to play that. It's going to take just a little bit to do this. Are there any questions so far? And you can see how long it even with our very sort of simple topography, it's still taking it a little bit of time to figure out how to chop off our block. There it goes. So now we have 2 volumes. Up here at the top, I'll select our volume. So we have the volume that we're going to throw away is volume 1. The volume we want to keep is volume 5. So I'm going to delete volume 1. The surface 7 was within the sheet body 2, so I'm going to delete that one as well. So there you can see now I have gotten rid of I've deleted my topography surface, and I have kept the top of the block, or I removed the top of the block that I didn't want anymore, that was above the ground surface. So now I'm going to take our subduction zone interface. You'll notice that it extends beyond the edges of my domain. That's because I need to be able to cleanly go through all the volumes. And so I'm going to web cut my volume 5, which if I come back here, so here's my volume 5 with sheet surface 8. That's the subduction interface. If you have realistic topography, sometimes the web cutting and so forth can take half an hour, even up to an hour. It's one reason why we said don't use more points than you need to define your surface. And that's another reason why, there aren't many mesh generators that work really well for geologic type problems. We're always on the lookout, so if you come across a mesh generator that, especially if it's open source or free, that works with well for geologic problems, we'd certainly be interested in creating an interface to it. So there it is. There you can see now I have a volume 5 and a volume 6. And so I'll delete my subduction zone sheet body. I'm going to keep both of these volumes because I want both sides of the subduction zone. Then I finally am going to cut web cut volume 5. That's the, so this is, I want to cut this volume with my splay fault. Well, exact edge, again, you have to define it well enough that Qubit knows that it goes past the edge. And so, exact edge is, I mean, if you have a line and it truly is a line, then you can be pretty confident that the tolerances it'll work. If it's a spline surface, then it's how well Qubit has, two splines with slightly different numbers of points, even if they look nearly coincident, they probably won't be exactly coincident. That's why Qubit is using splines, is because it can then, based on those splines, project the surface anywhere along there using those splines. And so usually it's best to have it go a little bit. And so the ways to do that are, one, you can, did it do it? Yeah. Okay, so I'll tell it, so let's delete it. And so now this was I don't like these dark colors. But so we had questions earlier about, imprinting. So here's, so here's my splay surface. And so I web cut, I just on last operation web cut these two volumes. The intersection of those two volumes on the lower volume, the lower volume does not know that that this interface exists because we web cut the top volume. And so we want to imprint that top volume on the other volume so it knows there's an intersection there, because we want that intersection to be honored by the mesh. So in here, when I do imprint all with volume all, that's what it's going to do. It's going to say, oh, I have internally defined this part, so that other surface that's there needs to meet it, and it'll subdivide so that the interface there honors that intersection. So Qubit simplifies the geometry when it's showing it. So you'll notice that it looks like there's little gaps. It does a pretty crude representation, coarse representation of the surface. But when we make the mesh, you'll see that our mesh is really honoring sort of our original curves. It went through the subduction zone. It did not penetrate very, very far. And so what oftentimes we'll do is we'll take that to extend our surfaces further than in areas where they may be defined. We'll usually take points and sort of project them either down along a contour or vertically, or, in some way we sort of put artificial points that sometimes we may do 2 points instead of a whole curve. But you don't want, if you want part of that curve, then it's going to influence the rest of your spline surface. So you need to sort of be careful how you treat the edges. Yeah, it did go all the way through. And so let's see. I think it looks like it did imprint. Yeah. But it's a little disconcerting when you look at this geometry. And look, it really looks like there's a gap here, and that's just how the resolution that Qubit used to generate in terms of the display. Underlying in sort of how it's storing it internally, there's a lot more resolution. So that's the geometry. And now we want to mesh it. So here's our mesh file. So in this case, all I'm doing is a discretization size of 6 kilometers, a TET mesh. And okay, so then, and I'm going to mesh the surfaces, and then I'll mesh the volume. And I think I'm going to, so it did it. I'm going to, so let's see here. I'm going to change to white. So there you can see my mesh better. You'll notice that now you don't see any of those little gaps, and you can sort of see the full sort of smooth, continuous spline surface there along where the splay fall hits the surface and where the subduction zone hits the surface. And then for tet meshes, you can do sometimes it's best, sometimes you can improve the mesh quality by having it flip some of the vertices and the connections, and that command is clean up volume all, and so you'll see that in some of our mesh cases, and then we'll smooth condition number 2 for all the volumes. So it did all the volumes. So we can go over here and do a mesh quality check. So I'm going to select mesh, select the volume mesh, select quality, all volumes. Let's do condition number, display graphical summary. So I do have, you'll notice that where the top of the subduction zone is coming up, that's where I have the porous quality. This is that case where I have a very, small angle, and so essentially by having such a small geometric feature, my sort of condition number becomes up to about 3. Everywhere else, my condition number is generally around 1. So one way to deal with this is to come in here, and essentially if this is my discretization size, if this is sort of the scale length, I can come in here and I can put in sort of a vertical line right in here to pinch off this last little triangle. That's sort of an approximation that when you're pinching off scale features smaller than what you can really resolve. The other way to change this is to sort of tweak the mesh geometry right around here. Either change the topography, have the topography sort of, you could have the topography sort of dip down right there, so the intersection isn't at quite as small of an angle. Condition number 3 isn't great, but you could just choose to live with that. Yeah.
So this locally affects how well you read the solution. Does it propagate any areas further away from that point? So you'd be worried actually at a longer wavelength than just what the condition number says for that particular cell?
So generally it's that cell. It's a locally it'll be stiffer. So it will affect the solution locally. Globally, it'll affect the rate of convergence. So it's mostly the rate in a quasi-static problem. It's mostly the rate of convergence that you'll see, and then locally you'll have sort of a slightly stiffer cell in that local region. So your solution in that region won't be as accurate as what it would be otherwise. But I shouldn't say as otherwise, because if you change the geometry, you'd change the solution as a little bit as well. So, it's really trying eliminating the features that are smaller than the resolution of your mesh. You're approximating features smaller than the resolution of your mesh. So it's how do you choose to do that? Do you want to just live with it and have a slower rate of convergence, or do you want to change the geometry to remove geometric features that are really small to improve the rate of convergence so you get a faster solution, even if it's not more accurate? So this is our mesh. We have boundary conditions, so let's load up our boundary conditions file. So here we have 3 different blocks. We're going to do the plate, slab, and sediments. So each of our volumes, we're using a different block ID. So here's our blocks, our plate, slab, and sediments. So here's our, and here one thing you can do is like when I look at boundary conditions, I like to turn off the mesh so then I can, it's easier to see when I click on the node sets and blocks. So then I have a node set for the subduction zone. Display faults. And then the boundaries. I'll run these and I'll come back and we can talk about some of them because you'll see that what's going on here. So I have a number of node sets. So I always like to check my node sets to make sure that I get the full faces that I'm expecting. So there's face X positive, face X negative, Y positive. So I got all of that. Face Y negative, face Z negative, yep. Face Z positive, yep. I got my subduction zone faults, splay faults. And you'll notice that in my splay faults, it's sort of hard to see, but right here there's no point right here along the intersection. So in order to handle fault intersections at this point, I can't have a node that's on, or vertex that's on two different faults. And so when I created my node set for the splay faults, I created a group that said add the node in the surface 30. That was for my splay fault. Then I said group remove node in group subduction zone fault. So I removed the nodes that are on the subduction zone from that group. And so that's why we use group. We can do Boolean operations on groups. You can't do Boolean operations on node sets. So once you create a node set, you can either add nodes or you can't sort of do these additional operations like add node, remove node. You can add, but you can't remove. And so that I do the same thing as Charles pointed out earlier for our boundary conditions. So I have like x negative. Come on. So I have like my face x negative without the subduction zone fault nodes. Face y positive. Here, let me do y negative without my splay fault or my subducting interface. In this case, that's because I'm going to bring those. Well, we're not actually going to run an example and a simulation here. This is just a meshing example, but this is if I was only doing slip on the interior here and I had the node set for those faults only being in the interior, then I wouldn't worry about these boundaries. But this is if I had a fault with flip coming all the way to the surface, or coming to the edges of the domain. And so that's how we created a simple subduction zone 3D model with two faults.